So I learned about quasars. All right. I was learning about quasars by reading this paper, and what pre-JWST means is everything that I learned came before James Webb. And I'll be explaining these terms, so don't worry if you don't understand what quasars and the Epoch of Re-ionization means. So just to give you like a short history of the early universe. So after the Big Bang, the universe was full of ionized helium and hydrogen, and there's also a little bit of lithium. Does anyone know what ionized means?
A different number of electrons.
Yeah. So originally, if a atom has all of its electrons, it'll be neutral, but when it loses an electron, it becomes ionized. So for example, hydrogen has one electron, so when it loses that electron, it becomes ionized hydrogen, and helium has two electrons. So that's why it's called doubly ionized helium. So in the early universe, the universe was very, very hot. So all of the photons, which are particles of light, the universe was very hot. So that means the light particles, which are called photons, they were constantly colliding with the electrons in the helium and hydrogen atoms, making those atoms ionized. So even if the electron were to recombine with its atom, just in a fraction, like a very short amount of time, like a photon would come and collide and make the atom ionized again. So eventually, as the universe expanded, the photons became redshifted. So this equation so first of all, what redshifting means is that the wavelength of the photon increases. So there's an equation here that says E equals HF. So H is a constant, and F represents the frequency. So as the wavelength of the photon increases, the frequency of the photon decreases, and E represents energy. So this means, as the universe was expanding, the energy of the photons was also decreasing. So this allowed the electrons to combine back with the atoms without being ionized. So I'll explain this a little bit more on the next slide. Okay, it's not here. All right. So this recombination happened in several stages because each atom has a different energy that it's required for it to become ionized. So for example, helium needs the most energy to be ionized, or to be ionized. So it was the first to start recombining, which was about 20,000 years after the Big Bang. And then later, helium's second electron recombined with the atom. And finally, hydrogen, about 380 years after 80,000 years after the Big Bang, its electron recombined because hydrogen, the energy required to ionize hydrogen is a lot less than the energy required to ionize helium. So, like I was saying before, the photons would constantly collide with the electrons in the atom, but now that the atoms become neutral and they recombine with their electrons, the photons that were originally produced by the Big Bang are now allowed to travel freely. So this is the light that we call the cosmic microwave background, and this is the oldest light in the universe. Okay, so during the Big Bang, I can't really explain why this happened, but there were some like quantum fluctuation. So what this means is that as the universe expanded and developed, the universe was not uniform throughout. There were certain areas that were more dense than others, and because of this, these overdense regions form the first galaxies and stars. So why this is important is because as these stars form, they reproduce the high energy photons that the universe lacked. Because the universe had expanded a lot by this time when the first galaxies and stars were forming. So there weren't really any of the high energy photons that could ionize hydrogen and helium. So that's why we call this the Epoch of Re-ionization, because when the first stars and galaxies formed, they produced these high energy photons that could ionize the hydrogen and helium. So I have a question for all of you. Does anyone know what the first generation of stars is called? All right, that is a pretty hard question. They're called population 3 stars, and I just wanted to point them out because I thought it's pretty interesting that we've never observed these stars before, but we believe that these stars were very bright and had much shorter stars than the stars that we see like locally. It's because these stars did not have the metals that the stars in the present day have, because these were mainly formed from pure hydrogen and helium. So because of this, the stars were not able to cool as effectively. And that causes stars to be very bright and have shorter lifetimes.
When you say metals there, you mean anything other than hydrogen?
Exactly, exactly. Yeah. Thanks for clear.
They're not really metals.
Yeah. And if anyone has any questions as I'm speaking, just please ask, because hopefully everyone can follow along with the presentation. All right, now just to give an introduction to quasars. So quasars are a specific type of supermassive black hole that exists at the center of galaxies. So generally, the supermassive black holes at the center of galaxies that are actively, the word is accreting matter, so they're taking in matter from their surroundings. Those are called active galactic nuclei, and quasars are the most distant and energetic type of active galactic nuclei. And just to give you a sense of the scale and how bright they are, the luminosity of quasars is thousands of times more than the entire luminosity of the Milky Way. And because of this, the quasars outshine their galaxies. So when we're observing the quasars, it's a lot harder to see their host galaxies because the quasar is just so much brighter than the galaxy it's within. And another question, does anyone know what might be brighter than a quasar?
Supernova.
Yeah, that's correct. Supernova is one of them. And another one is called a gamma ray. All right, another one is called a gamma ray burst. So what's interesting is that these are temporary, these are called transient events. So they're more temporary events that happen on much shorter timescales than quasars. So if we're talking about longer timescales, like in the span of millions of years, quasars are definitely the brightest. How do we detect quasars? So the most common method is something called a color cut. So a color cut method is where we're looking for objects that are more bright in certain bands of wavelengths and less bright in other bands. And what we're mainly trying to do is we're trying to search for objects that sort of look like points in the sky. Because quasars are so far away, they kind of look like stars, actually, which are kind of point-like objects. So the main thing we're trying to do is distinguish quasars from other types of stars. Specifically, the types of stars are called M, L, and T dwarfs. And one way we do this is, like I said, using the color cut. So the color of the quasar, it's more blue than the stars. So there's a large increase in the brightness of the quasar, around a wavelength of like about 121 nanometers. So when we're taking surveys of the sky, we're looking for objects that are very bright around this wavelength, and at other wavelengths are much more dim. So this is not the only way we detect quasars. There's also a few other ways we use to help support and make our and try to confirm whether an object is a quasar or not. Yeah.
You can tell it's a quasar because of the redshift?
Yeah, you can tell because of the redshift. Like,
Because if there was no redshift, you couldn't tell it was that far away.
yeah, the redshift, yeah.
Okay.
So the redshift is like, probably at least 2, I think, to be considered a quasar. So that's only about 2-3 billion years after the Big Bang.
Holy.
Well, yeah. Yeah, only because like we're 13.6 billion years past the Big Bang, so that's over 10 billion years ago. So another way we do it, so once we've like found a candidate for a quasar, the color cuts are pretty accurate, but they're not very accurate. So maybe about 40% of the objects we think are quasars in the color cut, we actually find out they're not. And the way we do this is by something called a spectroscopic survey. So originally, when we're making the initial cuts for whether something is a quasar or not, we're looking at the color, which is the brightness over a band of wavelengths. But to really confirm whether the object is a quasar or not, and like you were saying, like what distinguishes quasars is their redshift. And to get this value for the redshift, we need to take something called a spectroscopic survey. So what that means is that rather than measuring the brightness over a span of wavelengths, we're taking the brightness at each individual wavelength. So does anyone know why we might use the photometric surveys to initially decide whether something might be a quasar or not, and only then we go to the spectroscopic? Because you might think that you would just go straight to the spectroscopic if it's the most precise measurement.
Get an initial impression. It'll tell you if it might.
Mhm.
You can rule out a lot of the others.
Yeah. So yeah, that's a good idea. The reason why is because when you're taking the brightness over a span of wavelengths, you can get a lot more photons in a much shorter period of time. So each, like the detector, there's a specific noise level, and you want to get enough photons so that you exceed the noise level, and you can do this a lot faster and a lot more. It requires a lot less resources to do this if you're taking the photometric survey. A couple of the other methods is something called astrometry. So this is like looking at movements of objects across the sky. And one really easy way to tell if something is not a quasar is if you see the object move at all across the sky. Because like I said, quasars are like over 10 billion light years away. So it wouldn't be possible to see it moving across the sky. It's just too far away to see any movement. Another thing is the MLT dwarfs and the quasars, while their spectrum of light is sort of similar, the variation in the spectrum is a lot different. So the quasar's light varies a lot more than these other stars. So what this y-axis is, it's called flux. So you can think of this as like the number of photons coming in per unit area per unit time. So the brightness of the object, and this is the graph showing the brightness of the object at every single wavelength. So you might be wondering, like, why is there such a steep drop in the brightness? Does anyone have an idea? No? Okay. So what happens is, since these quasars are so distant, And like I said before, there was the Epoch of Re-ionization. So what happened was these quasars were existing during the Epoch of Re-ionization, before the Epoch of Re-ionization was over, which means that there was still neutral hydrogen gas that hadn't been ionized by the first stars and galaxies. So what that means is because there was this neutral hydrogen gas around the quasars, it would absorb the quasar's light at a very specific wavelength. And we call this wavelength the Lyman alpha wavelength. That's 121 nanometers. So maybe I do it. So that should explain why there's this sharp drop, because it's absorbing. Let me just. Anyways, it's absorbing at the Lyman alpha wavelength. But then why is there such a drop in the brightness at all of these wavelengths? So what happens is as the universe is expanding, the photon's wavelength. So originally there were these photons over here, which rather than being like 121 nanometers, maybe they were 60 nanometers. So what happened was, as the universe expanded, this photon that was at 60 nanometers became 121 nanometers, and then it was absorbed by the neutral hydrogen. So then all of the light that was shorter than this wavelength became absorbed by the neutral hydrogen. So this is something that we call like a Gunn-Peterson truck, and we only see this at quasars that are at high redshift, which means we only see this at quasars that were very distant. So does anyone know why this might be the case? All right. So as time went on, the gas around the quasars became more and more ionized because there was more high energy photons coming from the quasars, ionizing the area around it. More stars formed. So just generally what we call the intergalactic medium, that became more ionized. So what happens is, let's say we have a hydrogen atom, and it contains one proton. And if it's ionized, there's no electron in it. So it cannot absorb the photon's energy. But what happens is, at earlier times, like, for example, less than a billion years after the Big Bang, the neutral hydrogen still had this electron that was able to absorb photons whose wavelengths were 121 nanometers. So that's why we see only this sharp drop in flux at the higher redshifts. Instead, what we see at lower redshifts is that it becomes very spiky. And what happens is a lot of the light is still absorbed by these small pockets of neutral hydrogen that are spread out along our line of sight. So when we're looking through a telescope, we're looking through a line of sight to the quasar. And along that line of sight, there are these small pockets of neutral hydrogen. And the neutral hydrogen is very, very effective at absorbing any photons that are near the 121 nanometers. So what happens is that we still see absorption by the hydrogen, but then there's still pockets when there's no neutral hydrogen, so the hydrogen doesn't have the electron, so the light is able to pass through. There's some areas where the light passes through, and there's other areas where the light does not pass through. And this is called alignment alpha forest. And what's very interesting about this is that we can use this to try to figure out when the Epoch of Re-ionization ended, and we can try to figure out how much neutral hydrogen gas was really present over time.
What happens to the atom when it actually absorbs the photon? Is there any effect on the atom?
Yeah. So, um, wait, like, what do you mean by?
Well, you said the atom with the electron absorbs photons.
Yeah. So,
Is there any effect on the atom?
Yeah,
Does the atom do anything?
So what happens is this electron, let's say the photon comes in, the Lyman alpha photon with the 121 nanometer wavelength. This photon goes up to a higher energy level. So originally it's at the ground state. You could call this like n equals 1 energy level. Then it goes up to the next energy level, and it's there for maybe like a nanosecond. And then it drops back down to the first energy level, and then it emits a photon that is at 121 nanometers. So, like, why do you think this might not cancel out? It absorbs the photon, the electron goes up in energy level, then the electron goes back down at energy level, and it emits the exact same photon. So why is there still, you think, this decrease in the number of photons we're seeing?
You say that there's an effect on the photon. The photon that comes in is different than the photon that goes out.
Right? It is. The photon that comes in disappears.
Right. Okay.
But it still emits a photon. But the thing is, when it emits a photon, the direction the photon is emitted in is completely random. So only a very small fraction are going to end up going towards us. The rest are just going to be flying in other parts. An idea of like why the shape of it looks like this. So the quasar has something called an accretion disk. So that's an area of very, very hot gas that is swirling around the quasar. And what happens is that there's a lot of friction within the accretion disk, and this friction produces light. And there's this specific type of emission causes a shape that sort of looks like this. So most of these photons are coming from the accretion disk. Another area that contributes to some of this brightness coming in is called the broadline region. So this is outside of the accretion disk. There's more dust and gas, and that's absorbing the quasar's light and then re-emitting it in the more infrared wavelength. So infrared is like, for example, you have the X-rays and UVs over here at the shortest wavelength. Then you have the visible wavelengths. Then you have the infrared, and then finally the radio. So the broadline region, which has the dust, that's mainly emitting light in the infrared. And another very cool thing that you might have seen is that these supermassive black holes have jets. So these are caused by the electric field produced by the quasar, and they accelerate the electrons, producing light. So the jets produce light in the radio wave band, and about 10% of the quasars we see are what we call radio loud. What radio loud means is that they emit a lot of light in the radio waves, and they emit about 1,000 times more light in the radio waves as radio quiet quasars, which make up about 90% of quasars. One interesting mystery about these radio jets is that the percentage of radio loud quasars does not really change as you go further back in time. So let's say you were looking at quasars that formed 2 billion years after the Big Bang, you would see about 10% of them are radio loud. But then if you go back to about a redshift of like 6, so maybe a billion years after the Big Bang, you would still see 10% of the quasars are radio loud. So there are two things that could explain this. One of them is that 10% of the quasar's lifetime is spent in this radio loud phase. And another idea is that the radio loud quasars are just completely structurally different. Now is probably one of the most interesting parts. Hopefully you guys also find it interesting. Has anyone heard about the issue of the growth of quasars? No? So what the issue is that I think also James Webb brought to light a lot was that the quasars that formed became really, really massive, really, really quickly. So just a few 100 million years after the Big Bang, we see quasars that are like 1 billion solar masses, which is insane. And so how can we explain this growth? So what I found out by reading is that the only way this growth can happen is if you have these really massive black hole seeds. So if you start out with a really massive black hole, about like 1 million solar masses, and then for the entire lifetime of that black hole, it's constantly accreting matter at the maximum sustainable rate. There's a theoretical limit for the amount of matter it can gain per like the rate that it can accrete matter. It's called the Eddington limit. So if it's accreting matter at the Eddington limit for the entirety of its lifetime, only then can it grow so massive. Yeah. So you might be wondering, how do we even figure out the mass of a quasar? It's such a distant object. It only looks like a point in the sky. So what do we do to figure out its mass? Does anyone have any ideas about what we can do?
Can they see the accretion disk? Or they just see a point, the whole thing is just one little point?
I think with James Webb, you can get more spatial resolution. Right. But I don't think you can really make out the accretion disk at all. Yeah.
Maybe it's gravity or nearby our.
Yeah. So gravity is super important. So gravity is exactly how we figure out the mass. So there's this equation, mass equals v squared r over g. So v is just a constant, is a constant number. We don't really need to worry about that. It's called the gravitational constant. And v is velocity, and r is radius, and m is mass. So what this equation is telling us is, let's say we have some gas that's swirling around the quasar. So the gas has some velocity, and it's at some radius from the quasar. So if we know the velocity and radius of the gas, we can actually figure out what the mass of the quasar is, because the mass of the quasar must be something that ensures that the gas keeps on staying in the quasar's orbit. Does that make sense to everyone? Okay. So now the issue is, how do we determine velocity and radius? So I think one very cool method is, it's called thermal broadening. So I can draw another thing over here. Actually, wrong way. Okay, so this is another graph of the flux at different wavelengths. And rather than going over a large span of wavelengths as in this graph over here, this is concentrated at a very specific, just a couple nanometers across. So this is like about 280 nanometers, maybe like 278 nanometers, and 282. Well, this is like over several thousand nanometers. So there's a sharp like spike in the brightness. And does anyone know why this might happen at this like specific wavelength? There's a sharp spike in the brightness. No, so
You've got the accretion, this
Yeah.
spinning,
yeah,
some of it's coming towards you, some
Yeah.
going away, and that would redshift. or
yeah, that's
phase shift
that's
light.
literally exactly what I'm going to explain in a little bit. And that's the thermal broadening. But what causes the light to increase at this specific wavelength is, you know how I said the atom only takes in the photon at the specific wavelength of 121 nanometers? So it also only emits at these specific wavelengths. So what we see over here, this is the magnesium atom that is emitting at the 280 nanometers. So it's only emitting these 280 nanometer photons, but it's also emitting a little bit over here at like 279 nanometers and a little bit over here at 281 nanometers. And the reason why is because some of the magnesium that's in the gas surrounding the quasar is moving away from us, and some of it is moving towards us. So the gas that's moving towards us, its wavelengths shorten a little bit. So over here, there's some gas that is moving towards us at 279 nanometers, and over here, some of the gas is moving away from us. So the reason is like, let's say I have the magnesium atom here, and it's emitting these photons with some wavelength. If it's moving towards us, the wavelengths become shorter. If it's moving away from us, the wavelengths become longer. So if we use the width of this line, we can figure out actually what's the difference in velocity of the magnesium atoms that are moving towards us, and what's the difference in the velocity between that and the magnesium atoms that are moving away from us. So then, in our equation over here, we're able to figure out a value for the velocity. I would say the way we figure out the radius of this gas, so how far away this gas is from the quasar, is a little bit, it's not as interesting. I mean, it's not as interesting, I guess. So what we do is we look at how bright, it's specifically like how bright how much light is coming in at 300 nanometers. So this light is also created in a similar region. So, and the amount of light that's coming in is very strongly correlated with how far the magnesium atoms are from the quasar. So it's like the luminosity is proportional to the luminosity, the square root of the luminosity is proportional to the radius. So what we do is we measure the amount of light that's coming in at 300 nanometers, and we raise it to the 0.5 power to try to get a uncertain value for how far away the magnesium atoms, which are in the broad line region, are from the quasar. So the main issue with this is that it's not an, oh yeah.
Where did the magnesium in the first generation start?
So they weren't in the first generation, but after like the stars collapse into a supernova, they produced heavier elements, so that formed the magnesium. Yeah, so this produces, then we can get a value for the radius, but unfortunately, like, it isn't really a super exact relationship, it's just a correlation. So this causes us to get quite a bit of uncertainty in our estimate of the quasar's mass. James Webb will be able to get better spatial resolution, and we might even be able to see the gas around the quasar. So we'll be able to get a more direct measurement. Actually, I've gotten through most of what I was going to talk about. I have one more interesting concept to talk about, and we can go back to this. What this is called is an emission line. So we can go back to this emission line over here. And what's cool about it is that not all of this broadening is caused by the magnesium ions being different, like having different velocities. Some of it is actually due to quantum mechanics. So there's like an uncertainty in the energy of the photon that it's emitting. So sometimes rather than emitting photons that are exactly 280 nanometers, there's a very low chance, like several orders of magnitude lower chance that it's gonna emit photons that are at lower or higher wavelengths. So this is important because when we have a lot of neutral hydrogen in the early universe, we can actually see that some of the neutral hydrogen is absorbing photons that are at like slightly less than 121 nanometers or slightly longer than 121 nanometers. And using this broadening of the emission line, we can actually figure out the fraction of, like, we can figure out how much neutral hydrogen there is. It's a very effective tool for doing so because, like I mentioned over here, a lot of the light is absorbed. So it's very difficult for us to, like, let's say at 2 billion years after the Big Bang, most of the quasar's light around here is absorbed. And at 1 billion years after the quasars, the light is also absorbed. It's very hard for us to differentiate during which time period was there more or less neutral hydrogen. So if we have the like over here, there's some, it actually more looks like this. So some of this broadening over here is caused by the different velocities and also the quantum mechanics. So using this side of it, where the photons are not being absorbed, we can try to figure out how much neutral hydrogen there was. That part was a little quite complicated, so don't worry if like it didn't make too much sense. Hopefully it did. Yeah, I mean, I would have had another picture up here that summarized through these different studies by looking at these spikes in the flux and by looking at this width over here, how much neutral hydrogen there is at different times during the universe. And you would have seen that there's a really large uncertainty in the neutral fraction. Like I think between a redshift of 7 and 8, we estimate there's maybe between 20 to 80% of the universe is neutral hydrogen, which is a really large uncertainty. So it's very hard to study how much neutral hydrogen there is. But that's what cosmologists do. Does anyone have any questions? Yeah.
How many quasars are there?
Oh yeah, that's a great question. So I don't know how many there are, but I do remember that at a redshift of greater than 5.9. So when we're at a redshift of 6, we call that the end of the epoch of re-ionization. So at a redshift greater than 5.9, we've found 532 quasars. So it's quite a bit, but they're also like one of the rarest, definitely one of the rarest objects in the universe.
That's only the observable universe, which is a very small part
Yeah,
of the
yeah, yeah,
universe.
definitely.
So there's plenty more out there.
Yeah, but yeah, yeah, yeah.
So I've got a question. Are any quasars observed through gravitational lensing so that you get light from the same quasar coming from different points in the
Yeah.
sky?
Yeah,
Then
yeah,
you could compare the Lyman alpha forest
yeah.
for each one and see if the pattern was the same, which would indicate a more uniform distribution of neutral hydrogen at that.
Oh, yeah, that's a very cool idea. Wow. Yeah, I think like if you have a galaxy in front of the quasar, the galaxy you could see the gravitational lensing effect. Um, I think that would probably work. I don't really know about it, but it seems like an interesting option. And I do remember when I was like learning about gravitational lensing, that is one of the ways we look for changes in the brightness of the quasar. We study like the different images produced by the gravitational lensing, and we look at those over time, and then using that we kind of like are trying to find changes in the brightness because what the gravitational lensing does is it magnifies the brightness of the quasar, so it's easier to monitor those changes. Yeah.
Earlier you remarked that the gamma ray bursts in the supernovae can be brighter than quasars.
Yeah.
I imagine on average. You know how much like brighter?
No. Yeah.
And another quick question would be, when was the first quasar discovered? I don't remember you mentioning that. And was there any confusion at first as to what it was?
Yes.
Interesting story
Did you know about the confusion?
No, I just
Okay, because that's exactly like there was exactly a story about the confusion. So I think it was like in the early 1960s they discovered the first quasar, and the reason it's called a quasar is because it's originally called a quasi-stellar object. So they originally mistook the quasar for being a star, but later on we found that out that it was actually a black hole.
Hi, so I'd like to say something about the discovery of quasars. So they were just looked like another star in the sky, just lots of little tiny dots, as he said. But they discovered that some of them were producing radiation as well as light. So stars don't do that. So stars should not have radio, but these looked like stars and they had radio. So they were called quasi-stellar, which means looks kind of like a star, but they were quasi-stellar radio sources, not objects, sources. All right. And so that's what they were called for several years. But one of the people who studied them was Hongyi Chu from China originally. I worked for him for a while, and quasi-stellar radio source because there's R's and L's in it. So at one point he said, I cannot say this anymore. I will say quasar. And everybody in my group will say quasar. And so we all said quasar. And after the next conference, everybody else said quasar. Much easier to say.